Hi, I am Mohsen. I'm presenting 3D CNNs with adaptive temporal feature resolutions. While state-of-the-art 3D convolutional neural networks achieve very good results on action recognition datasets, they are computationally very expensive and require many GFLOPs. The GFLOPs of a 3D CNN can be decreased by reducing the temporal feature resolution within the network. For example, SLOFAS has decreased the computation cost by employing a high temporal resolution light pathway with a low temporal resolution heavy pathway. However, due to the various amount of changes across videos, the static temporal resolutions lead to unnecessary computational overhead. While the GFLOPs of a 3D CNN can be decreased by reducing the temporal feature resolution within the network, there is no setting that is optimal for all input clips. As we can see, some videos have high temporal changes and therefore require higher temporal information to be processed, while some have low temporal changes and therefore requiring less temporal information to be processed. In this work, we therefore introduce a differentiable similarity guided sampling module, which can be plugged into any existing 3D CNN architecture. SGS empowers 3D CNNs by learning the similarity of temporal features and grouping similar features together. As a result, the temporal feature resolution is not anymore static, but it varies for each input video clip. By integrating SGS as an additional layer within current 3D CNNs, we can convert them into much more efficient 3D CNNs with adaptive temporal feature resolutions. The SGS is a differentiable module to sample spatially similar feature maps over the temporal dimension and aggregate them into one feature map. Since the number of output feature maps is usually lower than the input feature maps, redundant information is removed as illustrated here. The important aspect is that output temporal feature resolution is not constant, but it varies for each video. In this way, we do not remove any information if there is no redundancy among the input feature maps. To do so, we need to A. Learn the similarity of feature maps, B. Group similar feature maps, and C. Aggregate the grouped feature maps. To learn the similarity of the feature maps, we map each feature map IT into an L-dimensional similarity space using the FS function, which is a simple neural network with two linear layers. After mapping, each input temporal feature map is represented by a ZT vector in the L-dimensional similarity space. To group similar feature maps, we use the magnitude of each vector zt, and we consider two feature maps similar if the value of delta t is lie inside the similarity bin. To make the grouping very efficient and differentiable, we propose a binning approach with b similarity bins. We set b equal to t such that no information is discarded if there is no redundancy between the feature maps of all frames. For most videos, a subset of bins remain empty. We first estimate the half of the width of each similarity bin gamma by computing the maximum magnitude delta max and dividing it by the number of the desired bins. Having the width of the similarity bins, the center of each bin beta b can be estimated as mentioned here. The grouping and aggregation of all feature maps based on the bins will be done jointly by sampling temporal feature maps which belong to the same similarity bin and add them together. To make the process differentiable, we use generic differentiable sampling kernels psi that are defined such that a sampler only samples from the input temporal feature map IT if delta t lies in the similarity bin B. Theoretically, any differentiable sampling kernel that has defined gradients or subgradients with respect to delta t can be used. In our experiments, we evaluate two sampling kernels. The first kernel is based on the Kronecker delta function, as mentioned here. The kernel averages the feature map that ends in the same bin. The second one is a linear kernel that is mentioned in the paper. After the sampling, the empty bins are dropped. In our experiments on the Kinetics 400 dataset, we showed that the similarity guided sampling can reduce the GFLOPs of a 3D CNN by over 47% in average, making a 3D CNN suitable for applications where they are computationally expensive. For more information, please come to our poster session, and thank you for your attention.